Welcome to all dear students in the lecture series on Solar PV Installer Suryamitra. Today we will start the second module, Basics of Solar Energy and Electrical Concepts. After carefully listening this session, you will able to know about energy from the sun. You will know about the what is solar photovoltaic and what are the other renewable energy sources. Now here we are going to dive into the heart of our solar system, the sun. Let's start at the center of the sun, its core. This is where the magic happens. The core is incredibly hot environment with temperatures exceeding 20 million degree Kelvin. That's over 2 crore degree Kelvin. At these extreme temperatures, something truly remarkable takes place, which is nothing but nuclear fusion. This is where isotopes of hydrogen, especially deuterium and tritium, combine to form helium, which is a noble gas. Due to the nuclear fusion reactions, an immense amount of energy is released. It's like a giant natural nuclear power plant. Heat from the core reaches to the surface by convection and then eventually reaches us by the radiation. While the core is where the action happens, it's not something we can directly observe. It is hidden due to the thick layer of hydrogen. The part of sun we can see is called as photosphere. It is the outermost layer and has a temperature about 6400 Kelvin, which is still incredibly hot but much cooler than the core temperature. Our planet Earth access to this energy for almost 8 hours throughout the day, all around the year. The entire ecosystem on the Earth exists because of the sun's energy, as we know, which is also we called as solar energy. The plant trees absorb this energy and this is then passed on to the animals, birds, and ultimately to the humans in the form of food. So every bite which we take is directly or indirectly the result of sun's energy. Beyond providing the food, the sun plays a crucial role in maintaining our planet's climate. It drives the water cycle, ensuring we have access to water from the rivers, lakes and oceans. Without the sun, our planet would be a very different place. So we can say that the sun is more than just a bright ball in the sky, but actually it is the lifeblood of our planet, providing us with energy, water and a suitable climate. Now we are going to delve into the one of the most fantastic topics in the physics, the dual nature of light, or we can say duality of light. The dual nature of light is a cornerstone of modern physics and it's essential to understanding the universe around us. The sun as the primary source of light for our planet is a representative of this duality. By understanding both the wave and particle nature of light, we can better appreciate the complex and fascinating world we live in. Historically, light was thought of as a wave. This idea was supported by experiments demonstrating phenomena like interference and diffraction. James Clerk Maxwell didn't directly contribute to the idea of light as a wave, but his work laid a crucial groundwork for understanding light as a wave. Maxwell's groundbreaking equation unified electricity, magnetism and light, which showed that the light is an electromagnetic wave. According to the Maxwell's electromagnetic theory, the energy is transferred from a hot body to cold body in the form of electromagnetic waves. These electromagnetic waves possess energy emitted by the hot body. Therefore, the change in electromagnetic configuration of atoms or molecules. The sun, being a massive ball of hot gas, emits energy including light in the form of electromagnetic waves according to this theory of light as a wave. These waves carry energy through the space and reach to us, allowing us to see the world around us. There are different types of electromagnetic waves. These are like radio waves, microwaves, X-rays. These all are the part of same spectrum but have different wavelengths and frequencies. Visible light is just a small portion of this spectrum. Decade later, it was Planck who introduced the revolutionary concept that would lead to the dual nature of light. According to the Max Planck's concept, the propagation of thermal radiation takes place in the form of discrete protons called quanta, and each photon having an energy. As we can see the equation for energy, and small h is the Planck's constant. The Planck was trying to explain phenomena of black body radiation, which is a classical physics couldn't account for the observed energy distribution of this radiation. However, as the science progressed, experiments began to show that light also exhibits properties of a particle. These particles are called as photons. The photoelectric effect is a classical example of this particle-like behavior, where light knocks the electrons out of the metal surface. The sun, in this perspective, is emitting countless photons. These photons carry energy and momentum, and when they interact with the matter, they behave like particles. Therefore, after understanding the dual theory of light in the simple terms, let's remember that the energy coming from the sun to the earth has two components, heat and light. Heat is nothing but electromagnetic waves, and light is nothing but photons. These light or photons are used to produce electricity through PV systems due to the photovoltaic effects. Now we will delve into the core material, crystalline silicon, used in the most commercially available PV modules, which is the backbone of PV module. Crystalline silicon is preferred choice for PV modules due to its abundant purity and versatility. As the second most abundant element on the earth, silicon is readily available source. Its ability to purify to extremely high levels is crucial for efficient electron transport. By carefully controlling the amount of impurities, we can precisely adjust the silicon resistivity. This property is essential for creating the desired electrical characteristics in a solar cell. Additionally, silicon forms a stable oxide layer, simplifying manufacturing process and enabling seamless integration with other components. Now take a closer look on PV cell production process. Here we can see that total 5 steps: polysilicon production, which is followed by ingot formation, vapor preparation, solar cell, and then followed by finally PV modules. Now let's discuss step 1, polysilicon production. First of all, question comes into the mind: what is polysilicon? Polycrystalline silicon, commonly shortened to polysilicon, is a purified form of silicon that includes p-type and n-type components. It is made up of multiple small silicon crystals which have been extracted from a rock type called quartz and known for its high crystalline nature. Polysilicon is highly pure and generates almost as much energy as pure monocrystalline silicon. Because of this, polysilicon is crucial to the solar industry as it plays a key part when manufacturing solar cells that are used in solar panels. It is also used in various electronic devices from smartphones to automotive electronics. The Siemens process is a common method for producing polycrystalline. For producing polysilicon, it was first developed by German companies Siemens and Wacker in the 1950s as a way to produce hyperpure polysilicon for semiconductors. The process has been carefully refined to bring polysilicon manufacturing costs down dramatically. With the help of resistive heating, slim silicon filaments are heated up to 11,500 degrees Celsius in a steel bar jar reactor. As we can see, this is steel bar jar reactor. The gas mixtures trichlorosaline and hydrogen pass over slim silicon filaments. The trichlorosaline has low boiling point of approximately 30 degrees Celsius, so it can be purified in tall desiccation columns relatively easily. Trichlorosaline deposits silicon on highly pure and slim silicon filaments and is heated by resistive heating until they grown polysilicon rods with a diameter of 15 to 20 centimeter. As we can see the photographic image of actual polysilicon rods. This step is called chemical vapor deposition (CVD) and is the most energy intensive part of the process. The long rods broken into small chunks. This method requires a closed loop system to recycle hydrogen and chlorine gases for efficiency and environmental reasons. Now let us take a look on second step, PV cell production process, which is nothing but ingot production. Now first of all, take a look on constructional details. This is a quartz crucible which is heated by carbon heater which acts as electrode. The heat shield is used to protect heat loss and which is surrounded by water-cooled chamber. To turn polysilicon into vapor, polysilicon is placed into the quartz cylindrical container which is heated until polysilicon forms a liquid mass. Then by touching a small crystalline seed to the surface of liquid mass and slowly rotating and pulling it upward, forms a large cylindrical ingot of monocrystalline silicon, as we can see here. Now take a look. Third step, vapor production. In vapor production, there are total 5 sub-steps, which are slicing, lapping, etching, polishing, cleaning and inspection. In slicing, as you can see, silicon ingots are sliced into very thin vapor using diamond coated wire saws. Circumference of monocrystalline crystal is ground down to a uniform diameter. Based on the resistivity desired by the customer, the ingot is then cut into the slices of around 1 mm thickness using the inner diameter saw or wire saw to form the vapors. After the vapors are slid, the process is called lapping, is performed to remove any saw marks and surface defects. This also thins the vapor and relieves it of the stress from the slicing process. After the lapping process, the silicon vapors are then cleaned and etched using the solutions of sodium hydroxide, acetic acid and nitric acid. Once the silicon vapors are clean, another process is known as critical edged grinding is performed to round the edges. This step reduces the risk of breakage in the later manufacturing steps. Next step is polishing. The surface of the paper must be polished to highly quality mirror finish. To accomplish this, the process must remove any micro cracks, scratches or other residual work damage. After polishing silicon vapors, followed by cleaning and inspection. Inspection, there may be visual inspection or by using particle analyzer and flatness gauges. After knowing the third step, now take a look into the fourth step and fifth step. Third step is a solar cell and fifth step is solar PV module. As you can see the image of a solar cell, it is defined as semiconductor device that directly converts sunlight into direct current, which is nothing but electricity. Now we can see the module. It consists of number of cells which are arranged in series connection, then by connecting series connection of the arrays to form a panel, and by arranging the panels either in series form or in parallel form, solar PV module array forms. Now take a look at the other renewable energy sources. As we can see, the hydropower, tidal energy, wind energy, geothermal energy and biomass energy. There are some advantages of these renewable energy sources. Those are, these renewable energy sources are inexhaustible, which means they will always available naturally in the environment. These energy sources reduces negative impact on environment since they doesn't pollute the surrounding like conventional energy sources like fossil fuel, coal, petroleum and petroleum products. It is an additional source of electricity, overall resource of the country. Renewable energy sources can be harnessed in the area which don't have access to the national grid or poor access to national grid electricity. In this way, we cover the first part of second module, and I'm sure that after listening this lecture, you are able to know about the energy from sun as well as you are able to know about what is the solar photovoltaic and what are the other different energy resources, renewable energy sources. Thank you.